we coming up on a quiz? But remember, use this time to learn your best way. Use these videos, use your book, use your lessons. Look at all those beautiful lessons that you can use to help you learn. Okay? All right. So let's go to the assessment because that's what I do. I like to grab your attention and say, look, this could be your problem. It could not be your problem. If it isn't your problem, the process is similar, if not identical. So just use your story, your problem to complete this. Look at those classmates. They were ready. They're like, I'm doing it. I'm jumping in. You always have 3 attempts. So you can also use your quizzes as like a practice because you can just take it again. I know that you writing them out, doing the thinking, you don't want to take it again, but it's the same as if you did the practice problems in the course. So whatever works for you is what I'm trying to remind you. That's the whole point of this time while I'm gone is how do you learn? Because after high school, and even maybe as a senior, it gets a little stricter, right? Teachers expect a little more independence, especially in college. So take this time to kind of figure out what works for you. Cool. Which probability distribution table reflects the data shown in the bar graph? Graphs will never leave our lives, whether we like them or not. Cool. This is the bar graph. According to this, there's 3 red, 3 yellow, 3 green, 3 blue, and 3 gray, right? They're all even. It's a uniform distribution. They all have equivalent chances. So what does that mean? Here we go, busting out the draw on screen. So if this is like a frequency table or a count, and the bar tells me how many of red, yellow, green, blue, and gray are in there, great. I know it's not a probability table. Like you can use a graph to show you probabilities, but this is not one. Why? Because of this. The probabilities must be between 0 and 1, and they're not. So it's most likely a count. So now I want to add them all up. 3, 3, 3, 3, 3. So 15, right? 15. Well, there's 1, 2, 3, 4, 5 that have exactly the same amount. So does it make sense to you that I can immediately say it's 1/5 the chance for each of them? The probability for whatever we're doing with these red, yellow, green, blue, gray stuff is a 1/5 probability. You can see that by the total is 15, and for each one, there's 3. 3, 3, 3, 3. So they all have that actual probability with the amount, and it simplifies to 1/5. So it's the same. I don't know if that makes sense. Okay. So, so it's in a decimal. 1/5 is 2/10. You can use a calculator. You can type 1 divided by 5, and you will get 0.2. But you can also think about number sense here, friends. Let's think about our number sense. 1/5 is equivalent to 2/10. Well, guess what? That is the name of that number. It's not, the name of that number isn't 0.2, just like the name of this number isn't 1/5. That's how we describe it. The name of that number is 1/5. The name of this number is 2/10, and that's the same name as this number. They're all equivalent. Numbers have multiple representations, and it can be confusing. So we're looking for a distribution table that's full of 2/10. I bet it's going to be green and highlighted for us. Ha-ha! That's our probability distribution table. If you have a different variation, just do the same steps. Okay, so figure out your counts, how many altogether. If they're not uniform, then you're going to need to do the division for each one like we did in the practice problems for yesterday, depending on when you watch this. Okay. In a study, and you can always ask questions, keep those questions coming. I will answer them as soon as I can. In a study, the number of students who said math was their favorite subject is shown by age group. 95 students, 7 through 9, 105 were 10 to 12, 145 were 13 to 15, 220 with the ages of 16 to 18. All right, so real quick, just because this is a near and dear statistic to my heart, that's actually, depending on what these mean out of the total, the percentage is like, okay, maybe they only interviewed 100 of the 7 to 9-year-olds. So, or 7 to 9-year-olds. But actually, math is typically a favorite subject in the lower levels, and when math starts to taper off right around 8th grade. Between 6th and 8th grade is when we start to lose students' love and interest in math. But quite often in the elementary years, it is a favorite subject. It's hands-on, it's tactical, it makes sense to them, and it's fun because when you know how to do math, it feels good to solve those problems. So anyway, I try to change that the best I can within the confines of what's required of me in our curriculum. So just remember that. Keep thinking, keep trying. I will do everything I can to support your learning and your willingness to think and just have fun with math. It doesn't matter if we get the questions wrong as long as we're trying to understand. And I'll always give you credit for your effort. Okay, moving on. Which probability distribution table best reflects the data? Oh, why do they do that to us? Probability distribution table. Okay, so now we need the total, right? So we have some work to do. So I'm going to bust out our calculator and we're going to keep doing some math. Okay, so let me scroll up. Let me kind of make this a little bit smaller. All right, so we've got 95 students plus 105 students plus 145 students plus 220 students. Okay, so that's 7 to 9, 10 to 12, 13 to 14, 16 to 18. So they have a total of 565 students in this group. Probabilities then for each category, ages, each age group is going to be how many said yes, it was math, and how many for each group. So we'll start with 95. 95 divided by 565. Okay. So I'd round to 0.17. I would round to that. Look at that number. Then the other one is 105 divided by 565. Okay, I 0.19 probably. And remember it said best, so we're going to have to make a, best one, which one makes the most sense. 0.26, okay. And then, 0.39. Okay, so look at this. It should be going up slightly, like it should be 17, 19, 26, and 39, about like that. So you can always have your calculator as you scroll. So let's see what we can find. Yep, there we go. See? Very close. They're all right here. Okay, cool. Great. So that's very, very close to the numbers we found, and that's the probability distribution table that we would select. Depending on your problem, you're going to do similar steps. Remember, you're going to add up the total, divide by how many for each situation, and that gives you the probability. Oops, nope, let's do question 3. Which statement explains the table? Which statements explain that the table does not represent a probability distribution? Okay, can't be negative probabilities. Probabilities have to be between 0 and 1, and the total probabilities need to add up to 1. Exactly 1, not more than, not less than. Unless we're rounding, then we'll get really, really, really close to 1. So here's the one. Aha, look, they're being so sneaky. 5/3, it's a fraction, so at first glance, you may be like, okay, they're all fractions. But 5/3 is greater than 1. And then already, let's see. So then already when we add them, 5/3 is already greater than 1. So if we add another 2/3, we're at 2. Yeah, so this is way bigger than 1. So the sum of the probabilities is greater than 1, and one individual probability is greater than 1. We can't have that. The results don't matter. They can be negative. They were trying to trick you. This is just saying like, hey, if this was a valid probability distribution, the probability that you would get a -2 is 2/3. Maybe -2 is a good thing. I don't know. Okay. Like it could be a game. So the probabilities have different denominators. That doesn't matter. This is true. No probability can be greater than 1. The results are all less than 0. The results are just what we're saying the probabilities are for, right? We're just saying this is what we're telling you. Hey, these are the possible outcomes. Here's the likelihood that those will happen. Those can be anything, literally anything. The sum of the probabilities is 31/12. That's great. I don't know if that's true. So you might want to go ahead and add those up in Desmos. Does that make sense? Let's take a second and do that. Might as well, because I don't know. They might say something like that, but then be trickers, and it's not true. So let's just do it. 2/3, arrow over, plus 1/12, arrow over, plus 5/3, arrow over, plus 1/6, enter, hit this little fraction button. Yeah, it's true. So just check it. I don't trust these curriculum writers. And remember, it's not me versus you. It's you and me versus them. We're trying to win. We're trying to learn. And we're trying to get these answers right together, okay? Me helping you and you doing the thinking. Okay, moving on to question 4. We'll go back to variation 1. Ooh. Some vocabulary here. We call this the random variable x. So we need to do a brief mini lesson. So again, here's some definitions, graphs of probability definitions, but we do need that, and hopefully it's in your book. Okay, great. Do they tell us x? Yeah, x. We call it just the random variable. So I guess maybe they said it earlier. I'm going to pause, and I'm going to see if they have it. Okay, so I don't think they formally, yeah, right here. So right here, the letter X is often used to represent a discrete random variable. For example, when a coin is tossed, the variable X would represent the two outcomes, heads or tails. They're both discrete and random. So we call it the random variable X. It's just a placeholder for like heads or tails, right? So this is a placeholder. X is a placeholder for patients, something with the patients, the number of patients. So we just say the probability that X, the random variable X, is greater than 0 but less than 30 would be all of these. That lets us do some math when we use that random variable X. It's just a placeholder for whatever situation we're talking about and whatever we want that to be. So that's just notation. We do need to start practicing that. That's going to be the hardest part for you guys to kind of work through independent of me, which is why I would check out your course. I'll do my best in these help videos to help you understand what that is, okay? We do have a concept of discrete, which means there's like gaps, right? Versus continuous. We'll talk more about that. What does it mean to be discrete and continuous? It's the same thing as with graphs. If you remember what a continuous graph looked like, we can draw it without picking up our pencil, whereas a discrete or discontinuous graph, we have to do dots and stuff. It's anyway, kind of. Okay, so good. Think about it. Must satisfy both. Those are the definitions right there. We hit that one hard. Good. Okay. So that's good for now. X stands for the ages of individuals of the staff members. See? So again, it's just a placeholder. Most letters are variables, meaning we just use them as a placeholder, just like in algebra. So that's what that's saying. So now, what is the value of P x equals 4 or x equals 1? We did some ors. It's just the same. So instead of writing the probability of 4 or 1, right, which remembered from our notation, that's just the probability of 4 plus the probability of 1. And since they're mutually exclusive, they don't overlap, we don't need to subtract anything. It can't be 4 and 1 at the same time, so we just add their probabilities. Okay, the only difference now is we've introduced the random variable X for notation purposes, but it means the same thing. So keep that in mind. So that's what we're going to do. We're going to add them. So the probability that it equals 4 or X will be the sum of the individual probabilities, just like we did before. So that should be that plus that, so 0.2, right? 0.15 times 0.05, or 15/100th times 5/100ths is 20/100ths, or 2/10ths. Use a calculator though. Any questions, whatever variation you have, just like the or events in Unit 5, find the probability that it equals 1 or the probability that it equals 4, add them together. If there's an overlap, then you would subtract it, but the odds are they're going to be mutually exclusive. Okay. Last question. The spinner is divided into 4 sections. The spinner is spun 100 times. The probability distribution over here, so they can give it to you in a table of values, they can give it to you in a chart, but they're telling you this graph is a distribution. And look at this. They're all between 0 and 1. And I bet if you add up all the heights, they'll add up to 1. Ooh, what is the probability that the random variable x, usually it's a capital there, not a small one, but it's okay, is between 1 and 3, including 1 and 3. So see that symbol? It's coming back. It's coming back. 1 is greater than or equal to, that x, the random variable x, is greater than or equal to 1, but less than or equal to 3. So we're going to come over here, and we're going to do the exact same thing that you think we would do. Well, first, I guess, think, what should we do? They're asking for the probability that we pick something greater than or equal to 1, but less than or equal to 3. So let's just look at this table. Well, this bar is 1. Can we have 1? Yeah. Well, 2 is between 1 and 3, okay, and 3 is less than or equal to 3. So those are the bars I want. Well, the probability, that's it. That's everything. I'm just going to add them up. So I read it. So this is 0.33 plus 0.15 plus 0.42. Here we go. This is 48, right? I did some mental math there. 0, 1, 0.90. Let's check it. Let's check it. Look, they're very sneaky. So we have a 90% chance of that happening. Whatever this represents, we're very likely to have a number between 1 and 3. 1, 2, or 3, right? Let's take a look at this, see what it hits. Okay, I would definitely say that's approximately 0.1. Why does this check help me, right? I would expect it to be 0.1 or 0.10, 10 hundredths, 90 hundredths, because when we add those, we get 100 hundredths or 1. Remember, the whole probabilities need to add up to 1. So that's a good check, and there it is, 0.9. It shouldn't mark you wrong if you type 0.90. You don't have to put the zeros unless you're speaking in terms of like money. Money, we put the pennies place. We put the hundredths place. That's it, you guys. Thank you for watching. And hopefully these help. If you have different variations and maybe something I didn't cover, please ask.